Hi everyone. Today's topic that we're going to turn to is to start to investigate practical Markov chain Monte Carlo methods. And our goal here is to kind of equip you with the tools needed to actually run some data modeling exercises using real MCMC packages. Now we're going to focus on those packages that are available through Python. These are the ones that I think most people in the class are using and are probably the most functional, accessible, free toolkits that we have. And hopefully if you're using a different language like MATLAB, you have kind of equivalent tools and the general framework will give you the insight that you need for doing your own applications here. Now, previously we set up and motivated why we need a Markov chain Monte Carlo method, and then we did some exploratory basics of what an MCMC toolkit looks like. Now we want to kind of get real and get into like what the industry standards are for doing this kind of modeling. This is really just an introduction. I'm going to recommend that you go and explore the documentation on the available packages. That fills out with much richer set of examples. What we really want to do is just give you the toolkit that's necessary to interpret the documentation so that you can take sort of what's available there and extend it off into the tool, into whatever problem you're trying to solve. So we're going to take two different approaches. The first approach is we're going to work with probably the simplest framework, which is a case where your log probability function is known, but you don't know anything about its derivatives. Here we're going to use a package called MCee, but there's another kind of related, not necessarily MCMC, but similar toolkit called Dynasty, which is a nested sampling algorithm. And these are cases where you can write down your log probability functions really effectively, but you don't know too much about like how to efficiently optimize those. The other case that we're going to rely on is cases where we can build up a data model through a bunch of primitive components. And so we can make a fairly sophisticated data model, but then because of the components having kind of computational awareness, they're able to use very sophisticated samplers. And that here we'll be using the pymc framework. But this is closely related to kind of the industry standard in MCMC and Bayesian methods, which is a package called STAN. That's non-Pythonic. It has some wrappers to it, but pymc at least gives us an introduction to the framework of how to sort of think about these things. And they're kind of two different approaches. I think as physicists, we're really used to thinking about things on the log probability function and write everything down into a single function and then kind of evaluate it as an optimization-like problem. So we're going to actually spend most of our time working on the thing that we're not as used to, so that's pymc. So let's return to one of our standby problems as a way of exploring these two cases, which is, of course, linear regression. So as our first approach, we will kind of want to take our basic linear regression model, which is, just a single univariate regression with a slope and intercept and an unknown error term here. We have a set of data, X and Y, and noise that is distributed from the normal, and each datum is going to have its own noise variance that we will, for now, assume is known. It can be unknown. And so we already wrote down that we can predict Y given the just sort of log likelihood or the likelihood expression. And then we end up being able to turn that into a posterior determination of the slope, the intercept, and if unknown, the noise uncertainties here by evaluating what this log probability function is. So we have this toolkit already in place. We're deeply familiar with it. And this is kind of what we would need to implement if we went and did our linear regression problem using an MCMC sampler. So we have our regular data set here, our standard XY bivariate data. We're going to assume only errors in the Y direction here. And we want to talk about how to actually implement this model in the case of this linear regression problem. Well, first is we're going to go and import this function called emcee. So you can pip install this, and you'll get this package here. The MC package, it uses what's called an affine invariant MCMC ensemble sampler. It's developed by the statisticians Goodman and Weir, and all this function really needs is you to define a log probability function. So we're going to do that. We first off set up our prior function on parameter vector. I'll call that parameter vector theta. And so M and B are going to be the parameter components theta. So it'll be a 2-element vector where M is the first element and B is the second element. And then we're going to just define that our slope should be 0 to 4 somewhere. That's kind of reasonable. We know it should be about 2 from our prior work with this data set. And then we'll assume that the y-intercept is somewhere between negative 50 and 300. Then return a good 0. Otherwise, if you're outside that bound, return negative infinity, which just means you're outside of the prior. So it's a lot likely you're going to actually see this. You're not going to actually have, you'll have 0 probability of sampling out there. So then what we're going to do is we're going to say, okay, we need to define a log probability function. It's going to take as inputs the parameters to the function. Then we're going to take x, y, and then the error, which I'll just call sy for sigma y or something like that. And then we will say that the log probability starts out with the log prior of the parameter vector, which will return 0 or negative infinity, depending on where those parameters are. We'll pull m and b out of theta. And then we will say that the error squared is whatever sy is here, quantity squared. We develop a model, mx plus b, and then we say, write down the log likelihood function here, which is, we're going to say it's minus 0.5, and the sum 2 pi log sigma squared, plus the error term, y minus model squared over sigma squared. And then we add on to the log of the prior, and this just returns this single scalar valued function. So if we're given MB and a set of data, we return the log probability. So that's how we implement the log probability. And all we need then is to set up our MCMC sampler using the package MC. So we'll import MC. And what we need to do is we need to define the dimensionality of the problem and how many walkers there are. So these are the number of independent, quasi-independent Markov chain samplers that we're going to do. This can be huge. In general, you need it to be larger than the number of dimensions you have. You generally are going to want it to be 10 times the number of dimensions that you have. So we're going to start off by building an initial random parameter vector. And so we're going to do np c_. If you don't know, this basically does a column concatenation of two one-dimensional arrays into a two-dimensional matrix or array. And then we say, okay, give me some random numbers that correspond to the number of walkers. And this is going to be initially my slope. So I'm going to say, okay, scatter it with a range of 0.5 centered around 1. And this will throw some walkers down to negative infinity because it will be outside of our slope. That's okay. They'll just sort of start out and try to walk to a good part of the parameter space from there. And then the second part is the distribution for the intercept. So we do a large scatter around the central value of about 100. So these are just guesses that we get from the data. The initial conditions are kind of important. If you started off super far away from where you're going to expect, you may actually not end up being able to walk towards the maximum probability space. So you do want to kind of put in reasonable values here. You also want to span a reasonably large space so that it can kind of start to focus in on the actual local maximum of the absolute maximum of the probability space. Okay, so that's all set up. The preface here is just defining log probability, setting up our initial conditions, and then everything that we need to worry about right here in the sampler, or everything we need to do to run the Markov chain Monte Carlo is in this single line, which is the mc.ensemble sampler. So this instantiates a sampler. And we tell it it's going to have 10 walkers spanning 2 dimensions, and then we give it the name of our probability function. And then we actually have to tell the probability function it's always going to take the parameter vector as the first argument to it. And then we say the rest of those arguments get passed as a list here. So that's the x data, the y data, and the error. And this list is just going to go and get inserted in. So anything that comes in here will be passed to the log probability function as the second through nth arguments there. And if you have keywords, you can also pass a quargs list that goes here, or a dictionary. A quargs dictionary will go here. And then you just say, okay, the result is the sampler run MCMC, so do the Markov chain Monte Carlo, starting at the initial conditions for 1,000 steps. And you just let it run. And the result spits out a bunch of chains. And the result looks like this. So these are the 10 independent walkers walking around, and this is the slope that they start from. So a lot of them started out spanning this region here, and they all quickly kind of move up and they converge to walking around 2.2, which is about the slope value here, as we go through the 1,000 steps. Similarly, the intercept drops down from the huge range that we gave it and quickly converges to the value that we are expecting, somewhere around 30 or so here, and we get the convergence. So if we ignore the first few samples, we can make a plot. You can tell that this is where it's doing its burn-in step, and then after about step 50 or so, it's sampling the posterior pretty effectively. Now we get a corner plot here. This shows the slope versus intercept as density space, and these are the projected marginal distributions. And you can infer from here the kind of peaks of the slope and the intercept, and that gives us a nice bivariate relationship. So this looks like a fantastic result. We've done good MCMC, we've got the slope and the intercept that we expect. Everything seems to be working, and we can get some confidence in that by checking our results. So with that set up, we now can start to look at how do we know that MCMC converged to a reasonable answer. Step one is often just look at the chains. They're right here. So go ahead and take the information and see that you see something that looks like it's spanning a constant distribution or a sort of a well-defined distribution, and things are kind of walking around inside that. You can also get a sense of this statistically. So the first thing that you often want to check with an MCMC run is to look at the acceptance fractions. Those are the fraction of proposed steps that are actually taken. So it proposes a step, and then it checks the probability, draws a random number, ratio of probabilities. It draws a random number and compares that to the difference in probabilities. And that acceptance fraction should be roughly between 0.2 and 0.8. If it's larger than 0.8, you're not proposing enough bad steps, and so you're not necessarily pushing out to these low probability parts of the distribution effectively. Or it indicates that you haven't yet reached the local maximum of the probability space, and so you're not actually doing proper sampling. You're still in the kind of convergence and optimization stage of the MCMC. So too high is bad. Too low indicates that your runs really are not effectively stepping at all or making good samples. So you're making all these steps, but you're not actually kind of walking around. Now, anywhere within that range is largely acceptable, and it depends on the dimensionality of your problem. So we can see for this particular run, which is only a two-dimensional problem, the acceptance fraction for these 10 walkers, you just call, it's a property of the sampler once you're done. You say, what's the acceptance fraction? And for these 10 10 walkers, we got a constant about 0.7, 0.72 as our acceptance fraction. That's very reasonable for a two-dimensional problem. We feel like we've done a pretty good job. If we see a low value, it's often one of your walkers gets stuck, and you can sort of see that it's not actually providing a good sampling. The next thing we want to check is a property that's called the chain autocorrelation. So what I've done here is I've taken a chunk of that good chain and I've zoomed in on it. And the point that I want to make here is that a lot of these walkers aren't actually walking very far, and often because they're only taking good steps 70% of the time, they're duplicating entries. So you can see from step to step, there's often just like it's a flat line. And so what this is doing is it's putting the same value into your posterior distribution multiple times. So this value down here from this walker is going to put 2 extra points in here. And so that means that the results in your distribution aren't actually independent. The way you would want sort of a bunch of random variables drawn from a distribution to be. They are not, independently distributed. They are, correlated here. This is intrinsic to the MCMC process, which is each step depends on the previous step. So it's not surprising here. And what we want to do is we want to really sort of treat things statistically like ignoring that kind of correlation from one step to the next. We want it to be a independent, identically independently distributed data. So what we need to do is kind of figure out how much redundancy there is in our chains, and then we can, if we want to, eliminate it by sort of stepping and taking only samples of the data every n points where n is sufficiently large that essentially any correlation with the previous sample from the chain is going to be completely independent. And the way we do that is we calculate the autocorrelation function. So that's essentially you take the chain and you just slide it with respect to itself, and you calculate the typical difference, and you just sort of look at how that falls down as over time. Or sorry, you multiply the chains in the autocorrelation. And so you just look at how that decays away to a point where if the chain is slid far enough along, it will have no correlation with itself. It will have lost all evidence of kind of where it was in the sampling because it sort of walked it far enough to be independent. And then once you're past that autocorrelation time, you know that samples separated by that are sufficiently independent that you can treat them as independent data. Fortunately, the MC package just calculates this for us. It has a little convenience function that's called sampler.getAutoCore_time, and it calculates how long that is. And if you do this, it's about 34 steps for slope and 33 steps for the intercept. Now, if you want a good sampling, you kind of want a chain that's about 50 times as long as this autocorrelation length. And you'll recall that we ran 1,000 samples, so 1,500 is kind of what we want for our number of samples. So we can actually take the sampler and run it for another 500 or 1,000 steps, and that'll ensure that we've really independently sampled the data. So it's good to sort of look for having chains that run 50 times their autocorrelation length. And the autocorrelation length can be significant just because it's not necessarily walking the full depth of the full width of the probability of distribution each time. Okay, so that gives us 2 tools. That's acceptance fraction and autocorrelation time. The third thing that we use is a statistic that's fairly common in MCMC methods, and that's called the R-hat statistic. And the idea behind this is that you want to look and compare the variance within single chains of MCMC to the variance between the chains. So that means that essentially you want each chain to be providing if this is true, it gives you evidence that each chain is independently sampling the full distribution function, and you're not off, and it's giving you the same answer no matter what chain you are using. with the MC sampler in particular, it's important that you actually run 2 independent runs before calculating things like this statistic, because while the chains look independent, they are not actually completely independent, given the way the affine invariant sampler runs. So run 2 chains, or run 2 samples through HIT before trying to calculate this R hat statistic. So how do we do that? Well, we're going to assume that the variable xi sub k represents some variable, random variable, is the ith sample in the kth chain of length n, and there's a total of big K chains. So we have each of this xik is just for one sample here. In this case, we had 1,000, n was 1,000 for our previous run, and then k was 10 separate chains. Remember, we have to run twice, so maybe we'd get 20 chains or something like that. Okay. So the variance, we calculate the variance within the kth chain. That's just basically you take the data, you calculate the variance along the length of the chain here. And so that gives me some measure sigma k squared. And then we calculate the mean of that variance, and we'll call that W, which is the within chain variance. It's the average within chain variance. And so that's averaged over the K chains of this per chain variance. So then what we do is we calculate the variance of the means of all the chains. So we calculate the mean of each chain. So you sum along length, you divide by n, and that gives me x sub k. And then I calculate the mean of means, and that's x. Sorry for the horrible notation. It's x bar bar. So you calculate the mean twice, so over the k chains. You calculate the variance of that value, and again, you apply the Bessel correction that gives you the between chain variance, and we define the parameter b here as n times sigma b. Now notice that this n is trying to reflect that this is in some sense the error in the mean, or the variance around the mean. And we want the full kind of between chain variance here, which is kind of comparing these different means. So we scale it up by the number of data, and that gives me a factor of b. So these should be of order the same. So if things are well behaved, so w and b should be about the same value. Then what we do is we compare W and B. So we have the the within chain variance and the between chain variance. And then we define this statistic, R hat, here I'm just reporting the square of it, which is the ratio, it's n minus 1 over n plus 1 over n times b over W, so between chain over the within chain variance. This particular, it seems like you should just be able to compare B to W, and that should be okay. But what's happening here is that this particular statistic can be shown to be following a specific distribution, and then you can actually make predictions on whether the value that you're seeing is anomalous. So that's why it's sort of formulated this way. It sort of roots back into the proposal of the statistic in the literature. I think it follows the student's t distribution, and it approaches 1 from the positive side. So it gets closer and closer and closer to 1. As you can see, as number of data grow large, you should have that R hat goes to 1, because this term should basically vanish as n gets large. So that's the hope. Generally, when you're calculating R hat, you want it to be less than 1.1, ideally less than 1.01, and that sort of indicates kind of a well-behaved chain. And this is just where this metric comes from, and you can just calculate it directly and report R hat for your chain. Often functions often these MC packages will just calculate R hat for you. Now, what we'd like to do is use the framework of MC and return to the case of our linear regression model. But in this case, what we're going to do is we're going to assume that there's some intrinsic variance, and this additional extra variance, sigma squared, is going to be a free parameter. We'll lay down a prior that's an inverse gamma function with alpha equals 2 and beta equals 1. And in this case, we will, and then we'll use our standard log probability model for linear regression with the idea that this term here can blow up, or it can increase because of this free excess variance term. Let's go ahead. We do the exact same data set. We feed in the term, we feed in this additional model, and we get a corner plot that looks not nearly as nice. Now, you can look at this and you sort of see, okay, these are the distributions. There's some mess going on up here. And then you can sort of see that most of the data here are concentrated around this case where the log of this intrinsic variance term is relatively small, and the M and the B are kind of concentrated around the values that we'd expect, but we have these clear outliers. And you can look at the result and sort of take a look. Again, I'm modeling here in log of this intrinsic variance term, and look at the walkers, and you immediately see a bad walker right here. So this starts out distributed through here and then jumps up to a very large intrinsic variance. And essentially what's happening here is it's saying that the variance is very large and that spans the full range of the data. So it's a fairly likely case. It certainly explains the data well, which is like everything is explained by uncertainty. You'll also notice that there's these long stretches of flat that are really visible within the chain. And so you can tell it's not actively taking a lot of steps here. So it's not finding more likely scenarios that it can jump to effectively. So the other thing is you look at the rest of these chains and they're bouncing around a lot. You can see that it jumps up a bit here for log sigma squared, and then it falls back down. And there's maybe a lower envelope that's a very reasonable value here. But this is sort of indicating that your MCMC is not performing very well. And this is the kind of thing that you want to pay attention to. You can get away with this by, say, well, actually, I think that my term is down here. You can really start your initial parameters for your walkers with log sigma squared around 0.2 with a fairly narrow range, and it will probably walk very effectively right here. We just started it out huge, and we get a lot of sort of positive excursions that we need to watch out for. We can see this in the acceptance fraction really quickly, is that we've increased the dimensionality of our problem. So our acceptance fraction overall is going to drop down a little bit. So we go down to like 0.55 or so as a typical acceptance fraction. But then there's this one walker, which is clearly our bad walker, is down here at 0.08, outside of our kind of acceptable zone and into the unfriendly territory. We can also run the autocorrelation time here, and we get reasonable values for M and B. But you'll notice that the log sigma, it's showing you that this isn't being very effectively sampled here. And part of that is because you have these large excursion points up here where it takes a while to kind of, if it jumps up, takes a little while to settle back down. And then this is not contributing very effectively either. It takes lots of steps to go and try to find another reasonable value. So this is saying that our chain is too short and we're sort of sending walkers off into low probability corners of the space that they can't get out of. They get stuck. So we've got some bad walkers here, and we'd probably want to revisit how we're doing this MCMC analysis. So this gives you some framework for understanding MC, the package. It's really pretty simple to get started. We were able to write down a log probability function, and the ensemble sampler just samples it. It's great. It just gives you an answer right away. And if you have complicated log probability functions, it works pretty well. And like you can stick anything into a log probability function. All it's got to do is return a scalar value that says the probability of these vectors is some value and hand it back. So it's great. You can attach it to external programs. You can do grid lookups. All these things live inside the log probability function. It doesn't care, which is fantastic. Disadvantages are the walkers get pretty stuck, and it doesn't work effectively in very high dimensional spaces. So as an example of that, I'll show you the MC sampling of a nice 5-dimensional Gaussian matrix. So what I did is I created a random covariance matrix for a 5-dimensional Gaussian log probability function, and I just told MC, go sample this Gaussian. And so it hopped around, and you can see every one of these corner plots, and looks like a nice bivariate Gaussian. This is a 5-dimensional Gaussian, so it's projecting through it in all of these spaces. And yeah, this looks like you're doing a good job sampling. Way to go, MC. If I take the exact same thing and then I say, well, do that by just changing my dimensionality to 32 instead of 5, things don't look nearly as Gaussian. And this is because it's not very efficient at sampling through and walking around in these spaces. And you start to get these weird kind of excursions off to these low probability spots that they can't then subsequently walk back to where the Gaussian should be located. So we have some issues once it gets into these high dimensional spaces. It can take a very long time and large number of samplers to really get down and start being effectively sampling in that space. So remember, always check your results. You just cannot blindly accept the MCMC is doing exactly what you want it to do. So this gives us a sense of how to kind of improve upon or what to watch out for. And often the remedies when you see something go wrong like this are to change the initial sample space, make it more restrictive or expansive, and then run for a longer period of time. So it will often settle down. It can just take a little while to get there. Okay, now let's change gears and talk about another package that's called the pymc package. This is a kind of standard package on that is much more sort of stats focused and stats friendly, and it requires kind of thinking and using the notation that the statisticians prefer, and that's a little different than what we physicists kind of really enjoy. PyMC uses either a no U-turn sampler, the nuts sampler, that's the first one. There's also a Hamiltonian Monte Carlo option as the second one. You can sort of activate either of these. By default, it'll just run the nuts sampler, and it's pretty effective at doing what it needs to do. And the neat thing about this is that those samplers are efficient because they have differential log probability functions. You don't actually have to differentiate it. You just have to build a model that the internal logic of PyMC can recognize and sort of do differentiation on for you underneath the hood. The approach that we want to take is to use this Bayesian formalism and notation to take advantage of the pymc framework. And it's very similar to this other package called STAN, which is kind of like core Bayesian statistics. And what better way to introduce the pymc framework than to use the linear regression problem? Well, in this case, we actually have to slightly rotate our thinking kind of 30 degrees for how we want to approach it. And what we do here is we say, well, in our linear regression model, what we're going to do is we're going to say that there is some observed distribution of data yi, and those data are distributed like a normal distribution with a mean that changes as a function of x. So we say that mx plus b is the mean of this distribution, and then sigma y is going to be the variance of that distribution. For simplicity, we're going to start out by assuming that sigma y is just one constant for right now. We can alter that, but in the teaching point, let's just say it's a single variance that's given in the data, or that is either given or not known. And what we need with MCMC is we will assert our priors on the slope and the intercept. We'll apply our Bayes theorem to figure out our posterior distribution. And I just want to highlight that sort of subtle thinking shift that comes from this, is we're trying to actually model the full distribution of the yi, recognizing that it has this kind of changing mean as a function of x. So we sort of think they are all drawn from this kind of like diagonal Gaussian pattern that is tracing out where those data are coming from. And then we want to figure out what the slope and the intercept of that mean variation of the Gaussian are. Okay. So what we're going to see in pymc is a framework that looks a little like this. I'm going to be a little more express about it. We'll import pymc, pandas, and then this other package called pytensor, pt. So that is a tensor computational package, and that's really useful for these kind of frameworks because you often have multi-dimensions and then extra data. So it does a lot of smart things with kind of bookkeeping, how to do mathematical operations on high-dimensional arrays of data, and that helps us a lot here. So we're going to need some convenience functions from pytensor. We're going to read our linear regression data, and we're going to get rid of those first 4 data, which are known to be outliers in our model. And then we instantiate something that's called a model class. So pymc.model. So we create a basic model, and then we're going to say there's some x data, which are these the data frame x to NumPy. So it basically makes the linear regression data into a NumPy array of x. And then we just say, using this kind of context of the basic model, so with the basic model as context, let's lay down our model parameters. So we say that B is a normal distribution with a mean of 0 and a standard deviation of 30. So sigma is 30 here. So the slope is a normal distribution with a mean of 0 and a sigma of 4. There's other priors we can do. We just sort of pick those priors here. And then we're going to say that the variance of the data is an inverse gamma distribution with alpha 2 and beta of 2. So from there, we say, all right, the mean, mu, is going to be some algebraic combination of B and M and the data x. So we just set that down. And because these m's and b's are these pymc functions, when we just do this algebraic operation, they are actually paying attention to the arithmetic operations of plus and multiplying and figuring out how these pymc objects are interacting here. When you multiply it by the data, it kind of brings them in, and x here is treated as fixed data set. And then we say we have these observed values. Well, they are normally distributed. You'll recall that's this normal function here. The m and b are the priors. That's what we've laid down. But this is the distribution we're talking about now, which has, we'll give it the name y_obs. It has the mean that we've calculated from our prior distribution of our random variables. Its width is going to be the square root of the variance. So pt, this is where we need the pytensor, because that's what gives us mathematical operations. So where we'd often go to like numpy.square root, we'll often go to pytensor.square root on the variance. That'll give us the width there. And then this one, we say we have observed data that are just the y values in the data frame. So this sets up my model, and then all I have to do is say, with the model, draw 1,000 posterior samples. I did is pm.sample 1,000, and it just goes along and does some sampling. You don't have to specify initial conditions. You don't specify anything at this point. And part of that is that it has sensible initial conditions. If you need to set initial conditions, you'll usually do that here in the sampling step here. So it draws samples from this data model, and then we can take a look at them. With pymc, we have this additional package that's called rvis, which is a visualization package, an analysis package for Markov chain Monte Carlo methods, especially those developed from pymc. So we import this rvis package as, and then we do as.plotTrace of the sampler data, and we just say, okay, go ahead and combine these all into a single plot. And it does so, and it shows me the density distributions for the intercept, the slope, and then the variance. And you can see the traces here. There's actually a bunch of different traces here. I think by default it runs 4 separate chains, and these are independent chains in the nuts sampler. So you can sort of see them bouncing around here. You don't see a lot of variation chain to chain. And otherwise, the samples look pretty good. And then you can do a corner plot on the results from the sampler, and you get a very familiar looking covariance plot with an estimate of the slope and the intercept. So that's how you would set up our linear regression model in pymc. I want to take a little pause here and talk about some of the toolkit, because this pymc framework is a little different from just like write down a log probability function, then sample from it. What we're doing is we're building a data model, and this is very well aligned with what a Bayesian style of thinking would do. One way we like to represent that is through this graphical representation of data models. And the way these are built is they're just sort of drawn as graphs in the sense of like graph theory, and they are directed acyclic graphs, I think is how you end up describing them, which just means that they're kind of a hierarchical model and there aren't any loops in them, and there's a sort of arrows instead of, links between nodes going in both directions. The general notion is we use circles here to indicate random variables. If we don't know them, we leave them unfilled, and then we shade them in if we do know those values, and they therefore provide constraints on a model. So a single datum we would sort of represent here with a shaded random variable. If we have a collection, we draw a little box around it to indicate that there's multiple, and we'll often put a little number down here to indicate how many of those random variables there are. And so this is a collection of random variables. And you use these boxes in cases where you have like 2 separate observed random variables and they're tied together. You can indicate that tie through this collection. So there'd be like 16 XY pairs in this case. So there could be a little 16 down here, and these are collected here. Then we use graph connections, are these arrows, just sort of indicating dependencies. And then if you don't have a circle around it, it means it's a non-random variable, and so it's just a parameter of the problem, or a hyperparameter of the problem. And so variables or distributions kind of can be here without elements without these circles drawn around them. So for the linear regression model that we just solved here, we have M and B here, and then we use sigma y as a unknown or as a known constrained parameter on the problem, and they all fed into a collection of measuring yi. We could also have I guess we let the sigma y vary. So what we should do is we should actually draw a circle around it. So if we assumed a sigma y, that we would no circle. A circle would indicate that we have a constrained variable, sigma y, and then we can write down what the hyperparameters are that we stuck in. We assumed a distribution on the slope, the intercept, and the noise in this case. So it was just normal, and an inverse gamma function. And so that sort of shows the construction that we've made here. We've also assumed x, so we can also say that the xi also just sort of feed right in here, but it's not a random variable, it's just sort of a constraint of the problem, so we didn't show it up here. The nice thing about this is these graphical models, once you've made them, you can actually just say to pymc, draw me the model for what you think this basic model is. And it will go ahead and tell you that the variance is distributed like an inverse gamma function, and M is a normal and B is a normal, and they all feed into a normally distributed y-obs data, and then there's 16 of those data here. So it'll just draw the model for you. And this is really helpful because you'll often write things down kind of in computer language, and you just want to check to make sure that the structure of your data model is correct. And this gives you a great toolkit for doing it. So we can go ahead and use this graphical representation to check and make sure what we think is happening is actually happening in the code. Okay, so we've learned a couple packages, just gotten the barest introduction to MCee and pymc. We've learned a little bit about testing the health of our MCMC from acceptance fraction and the R-hat statistic. In the next video, I'll focus on how to do this in the pymc package. And then we sort of developed a little bit of our intuition for using graphical models, which is, again, a very Bayesian way of approaching these problems, but also pretty powerful. So I hope that gives us enough to kind of get started. And I stress, this is really just to orient you as a first examples case for this. And you should really go and rely on package documentation as you start to really dive into, well, how do I actually apply these things to the problems that I am facing? All right. That should cover it for today. Have a good one.